Hello everyone. I hope your JEE Advanced exam on 18th of May went well. And now I'm sharing the detailed video solutions to physics questions. Let's get started. We are starting off with paper 1, section 1. Just a quick overview of this section. There are 4 questions in this section and each question has plus 3 minus 1. Plus 3 minus 1. If you do not attempt a question, you do not get any marks, okay? Neither negative nor positive. And all of these questions, all these 4 questions have only one option correct. Let's get started. Let's look at the first question now. The center of a disk of radius r and mass m is attached to a spring. So this small one, this is a disk. Its center is attached to this spring that is given to us. The spring constant is also given k. Inside a ring. Now this big circle that you see, this is your ring. And its radius is capital R, which is of course bigger than the radius of the disk. The other end of the spring is attached to the periphery of the ring. So this part of the spring is attached to the periphery of the ring, the circumference, one point on the circumference of the ring. Fine. Both the ring and the disk are in the same vertical plane. So this setup, you can say it's in one vertical plane. Okay, it's in one vertical plane. So let's call that the XY plane. The disk can only roll along the inside of the periphery of the ring. So this disk that you see, this disk, it can roll only along this path. Okay, it can go along this path as only. So along the periphery. And this rolling is without slipping. So one thing to keep in mind, rolling without slipping. Because we'll need the conditions for perfect rolling, okay? Rolling without slipping. Okay. Now, the spring can only be stretched or compressed along the periphery of the ring. So the spring also cannot stretch directly like this. The spring also can only stretch along this, like this, okay? If the disk comes here, this is how the spring will get stretched. And that is given to us. Fine. And it follows Hooke's law. So force is equal to minus k times x, where x is the stretching in the spring. In equilibrium, the disk is at the bottom of the ring. Let me clean all this up. So in equilibrium, the disk is at the bottom of the ring. That we can see. So right now, this position is your equilibrium position. Now comes the question, okay? Assuming a small displacement of the disk, displacement from its equilibrium position. So let's say from here, the disk moved here. Assuming a small displacement, the time period of oscillation of the center of mass is given, and you have to find the expression for omega. This small displacement we can quantify by an angle from the center. This is our reference frame or reference point. We will be observing the motion from this position. Okay, a small displacement of theta has happened, and the time period is given as 2 pi by omega. So when this theta is changing, so this omega is basically d theta by dt. So this is one thing to note. Okay, so we have to find the correct expression for omega. That means what is the angular velocity of this disk as it is moving along the periphery of the ring. Okay, so we have understood the question. Now let's get on with it. So this is going to be our approach. We're going to find out the torque equation about the center of the ring. Let's call this about R, which would look like torque about this R is equal to negative some torsional constant into theta, where theta is the small displacement. Once we have this, we're going to express torque as I effective, which is I about this axis of rotation, okay, into alpha. Alpha is going to be d square theta by dt2, or theta double dot. I alpha is equal to minus c times theta. So then from here, we can write what is angular acceleration, which is minus c by I effective, this into theta. And from here, we can say that this c by I effective is nothing but omega square, and we'll have the value of omega. Yeah. Let's now go step by step. First is we are going to write the torque equation. This is going to be our first step. The second step is going to be finding I effective. Once we are done with this, you can finally get the answer. Let's focus on the torque now. The forces that are acting and the forces that would be responsible for torque about this axis would be only two. One would be the gravitational force, and the other would be the spring force, the restoring force of the spring. Mg acting downwards, this is going to produce some torque. So the torque produced by Mg is going to be in the clockwise direction about this axis of rotation. Fine. Then there is going to be a torque produced by the force Kx, which is the restoring force of the spring. This is also going to be in the same direction, the clockwise direction. So when the object displaced from position 1 to position 2, the object is moving in anti-clockwise direction, whereas the torques are getting produced in the clockwise direction. So we'll have to put a negative sign to the net torque. Now, normal reaction is not going to produce any torque because the distance of the point of application of force from the axis is zero in case of normal reaction, because normal reaction will act along the axis, right? So that's why normal reaction is not going to produce any torque. So quickly, let's write the net torque expression then. Torque about this axis R is torque because of the gravitational force, which is mg sine theta. Since theta is small, we can write mg theta into the distance of the point of application from the axis, which is r minus r. This is the torque, and it is in which direction? In the opposite direction to the displacement, so we put a minus sign. This is the torque because of weight. Then the torque because of Kx, or the restoring force of the spring. This is going to be Kx into r minus r. That's going to be it. X, we can write this as, in terms of theta, we can write x as this. I'll write mg theta r minus r. The first term as it is, we'll take minus in the bracket, and plus k, instead of x, we can write it as r minus r into theta. So theta r minus r, and there is already an r minus r here, so this will become a square. Okay, so this is our expression for torque. Now the second step is finding I effective. This was our step 1. Step 2 is find out what is I effective. Now, very important, we cannot use parallel axis theorem to find I effective this time, because we are trying to find the effective moment of inertia about this axis passing through the center of the ring, which is not the instantaneous axis of rotation of the disk. So we cannot apply parallel axis theorem directly. So you might ask, why are we not writing torque equation at the instantaneous center of rotation? Then this problem wouldn't come, no? This problem of I effective wouldn't come. Now, we're not doing that because the instantaneous center of rotation itself is moving. If you see, for this small displacement theta, the instantaneous center of rotation has been moving from here to here to here to here to here. And this would make things more complicated. And that is why we are focusing on the inertial frame of reference, which is this. We're going to write the torque equation here. We're going to calculate the moment of inertia about this axis, and we'll be sorted. So let's now calculate the moment of inertia. So if not the parallel axis theorem, then what? Then energy considerations. You write kinetic energy expression in terms of I effective. This would be kinetic energy translation of the disk plus kinetic energy rotation of the disk. Notice one thing. This disk is translating along this with a different omega than it is rotating about its center of mass. So this omega, let's call it omega, is different from this omega. Let me clean this up and emphasize this point once more. This disk, the center of mass of this disk is moving along this with a certain omega, okay? D square theta by dt2. But this disk is also rotating about its center of mass, right? And this omega would be different from this omega, okay? So let's call it omega 2. But we can relate these two omegas, we can relate these two angular velocities because we know this is pure rolling. Coming back to finding I effective. I effective. So kinetic energy, writing from this axis, we can write half, whatever is the I effective that we have to find, omega square. Omega square. This is this omega we are talking about. Then we can write the kinetic energy of the system from the perspective of rotation of the disk itself, which is going to be kinetic energy translational plus kinetic energy rotational. Kinetic energy translational, it's going to be half mv square, where this v is nothing but r minus r into omega square, okay? Half mv square, this is it, plus the translational or the rotational kinetic energy. It's half. Now this is rotation about the center of mass of the disk. So I about center of mass of the disk and omega 2 square this time. Okay, this is going to be, this is the trick. So now you substitute the values and find out the value of I effective. I center of mass is what? Half mr square, small m, small r whole square. And what about omega 2? How do you write omega 2 in terms of omega? See, this is pure rolling. So we know that this velocity is the same no matter from which perspective are you looking at it. I can write omega 2 into small r must be equal to omega into capital R minus R. This would give us the relation. Okay, so here instead of omega 2, you can write R minus R upon small r into omega. And this entire thing's whole square is what you have to substitute here in place of this. Okay, so when you do all this substitution, you would get I effective as, I'm directly going to write down I effective now. I effective would be mr minus r whole square plus half mr square r minus r upon r square will get cancelled, whole square, and eventually 1 plus 1 by 2, it's 3 by 2 m r minus r whole square. Okay, so this is your I effective. This is going to be your I effective. We have to use this I effective where? In the expression for torque. Torque was, if you remember the expression, it was mg r minus r plus k r minus r whole square times theta. This thing into theta. And this we wrote I effective into alpha, I effective theta double dot. This is equal to mg r minus r plus k r minus r whole square theta. And I effective value you can substitute here. Yeah. If you do this, you're getting omega square as, so this comes out to be 3 by 2 multiplied with g by r minus r plus k by m. This is your omega square, and omega comes out to be under root 3 by 2 g by r minus small r plus k by m. So this is option A. That's your answer. Okay, option A. This is your answer.